All right. So let's take a look at the quiz. Um, so the quiz, don't remember how people did. I don't remember what the stats were like.
The average is like a 53.
Yeah, the average is 52.3, standard deviation 23. Yeah, all right. Okay, so let's take a look at how that went. Now, the first thing I did on here was I gave you a messed up version of the Peterson lock. Um, who here can see how it differs from a Peterson lock? And you can't answer. Yes, Baron.
The victim equals me thing.
The victim equals me thing. It should say victim equals me, not victim equals other. Right?
Oh, yes.
Okay. It should say victim equals me, not victim equals other. And the consequence of that is, let's think about how this happens, right? We have thread 0 and thread 1. Thread 0 comes in here. Me is 0. Other is 1, right? I set my flag to 1. I set the victim to 1, right? Now I say, while flags.getOther is not equal to 0. Well, the other's flag is 0, right? Because the other hasn't moved yet, hasn't done anything. So I've got the lock. Okay. Now thread 1 starts, and thread 1, me is 1, other is 0. I set my flag. I set the victim to 0, right? And now I say while flags.getOther is not equal to 0. Okay, so that's true this time, right? Because the other one has raised their flag. And now I say and victim equals me. Well, victim does not equal me because I set it to other. And so they both get into the critical section. So being greedy makes it not work. Being selfless and letting the other one go first makes it work. Just in real life.
It's that one the bang that makes it.
The thing that makes it not work is this, right? It's supposed to say victim equals me. That's the thing that makes it not work. Right? Because if you just follow the logic straightforward the way I just did for each thread, you'll see that they both get through to the critical section. And therefore, this is going to fail. Both threads can get into the critical section. That's going to happen. So that's the problem with this. Yes.
So why would you not need to call a flag.set to change it to 0 at the end?
You do in the unlock, not in the lock. You don't do a you don't unset the flag in the lock method.
So it would be the right answer.
It wouldn't.
We don't.
Correct.
I think for that it would be nice to have it like clarified, like consider this code only for the lock method instead of.
Well, okay, but public void lock, open curly.
Yeah.
Close curly.
Yeah, I see what I did now.
This is clearly the entire method. So that should be clear. All right. So, this is the thing. You have to understand the Peterson lock. We presented the Peterson lock. You have to see how it works. And when I mess it up, you have to be able to detect that. Because in the real world, you have to understand things at this deep a level if you're going to debug parallel codes. Any other questions about this one? Yes.
I thought instead of victim, it was more like turn. So I thought it was
all the examples that we've had All the examples that we've had has been called victim. Yes. Okay. Any other questions on the Peterson lock? All right. So this will get you used to the kind of questions that you might encounter here. It's a learning experience. Okay. And then there's some true and false questions, which are less tricky. And I figure, you should probably have done better on these. A Peterson lock is starvation free. True. A filter lock is starvation free. True. A bakery lock is starvation free. True. A bakery lock has a doorway interval. True. A bakery lock has a waiting interval. True. Finishing and serving interval. No, I just made those up. A filter lock can work for 10 threads. Sure. 100, whatever. Yes, Reagan. Yes.
Kind of be up at the top level of the filter.
No. Because what happens is, remember the way it works, right? We have a victim field. And whenever I try to get a lock, I set the victim field to me. Now, everybody that comes through there is going to set the victim field to themselves. So even if, like if I have 100 threads and the first 99 came through and I set the victim field to me, right? Even if the other ones jump back in, right? They're going to set the victim field to themselves. I'm going to get in. I mean, it may take a while, but I'm guaranteed to get in because of that victim flag. All right. Bakery lock can work for 7 threads. Sure. 1,000,000, whatever. And then I copied this question verbatim from the previous quiz. So this is a thing I do, right? So this is, if you get a quiz back and you miss something on it, make sure you know the answers, right? Because they can come back to bite you, right? Sometimes I'll give you the same exact one like I did here. Sometimes I'll put a slight wrinkle on it. But, you need to, one of the things I try to do, right, is I try to encourage you to stay on top of this course. You cannot fall behind. If you get behind, then you're dead, right? And nothing can save you. So I strongly encourage you not to fall behind. And this is one of the ways I can do it. So the pop quizzes, the repeated questions, and so on. These are all ways to try to prevent you from falling behind. All right. Any other questions? Tristan.
Do you think you can briefly explain the filter lock one more time?
Yes. Yes, Reagan has asked me to completely redo chapter 2. Does anybody else have a question?
I guess, could you re-go over doorway and waiting interval for the bakery?
Yeah, okay, we're going to go over. I'll try to breeze through chapter 2 again for you at some point, but I'm guessing you want to go over the homework first. Is that true? Yes. All right.
Any idea on how to start? Great.
Well, okay, on how to start the next homework is a different question. I'm going to talk about going over the one that we already turned in and was graded. Well, it's in the process of being graded. Yeah, Moodle won't let me enter the score on the same page where I enter the feedback. So, so some of you have feedback, but no score as yet. I'm working on that. Not usually, but I so far what I graded about 3 homeworks, and I don't think they need a curve, but we'll see. Yours is most of the way graded. All right, so dining philosophers. So I'll give you an idea what I was looking for from that one. Here's my version of it. Right. So I have a public class, dining philosophers. It has a constructor that takes, a number of philosophers. Now, the key thing that we're doing here is we're representing each chopstick with a lock. Okay. So if you pick up a chopstick, only one person can have a chopstick. So a lock is a good representation of that. I'm using a reentrant lock for that, like we always do. And I'm just initializing this in the obvious way. I have a dine method. In my dine method, I'm taking it takes an int with a philosopher number. So I'm going to say the left chopstick is going to be the philosopher number itself, and the right chopstick is going to be the philosopher plus 1% n, where n is the number of philosophers. So that gives me, if it gets to the end, it'll wrap around, right? And then I say if left is greater than right, then swap them. Okay, so that gives me a canonical order. Remember our rules for using locks? We always lock in a canonical order, right? And then I have this cool thing where I can print colors. So I have a philosopher is hungry. They get the lock. They get the left lock, the right lock. They eat. That's green. And then finally, they unlock and print their thinking. Okay. So that's the basic way this works. And I start with a number of philosophers. I create my dining philosophers class. I so there's a couple of different ways of keeping track of your threads. So I have this one that says this is the number of threads that are running at this point, and as long as the active count is greater than that, I'm going to wait at the end for this to finish. And all right, so inside this loop, I'm going to create a thread T. I'm going to say for I is 1 to 10, D dot dine. And then I'm going to print, after it gets through the loop, I'm going to say philosopher is done eating. And maybe I can pick a different color. Let's see. Let's see. Oh, I guess I'll stick with green. I thought I had cyan available to me. Maybe maybe I could just make my color class better. I don't know. All right. So let's run this thing. All right. So when I ran it, aren't those colors pretty?
Have you made your own class to do that, or?
Yeah, I pushed it over to the codes I give to you guys. It's just hold on. This one, console colors. And it's just got, some strings defined. All right. Okay. So anyway, that's the basic idea of how this works. You just have all the threads running, and they're trying to all dine at whenever they can. They get the thread, they get the locks in a canonical order, and that's all there is to it, really. Any questions about that? Okay. My red blue lock thingamajig. Yes. Yes.
Feedback says that I use sleep instead of condition variable.
Yes.
Is there any part in the directions that specifically should have clued me in that it should have been a condition variable?
Well, all of chapter 8, when we did condition variables for that purpose, right? That is the purpose for which we have them, right? And so you should have used it. So let's see. All right. So this one, I used a fair reentrant lock. This is the thing we haven't talked about it. It's not critical. It doesn't matter if you did this or not, but that's what I did. There are different kinds of reentrant locks you can get. You can, by default, they're unfair. You can ask for a fair one if you want to just increase your fairness of your whole method. But you can regard getting the lock as a doorway method, and putting a false there is fine. Okay, so I have a lock and I have a condition. I defined red running, blue running, red waiting, blue waiting, and I defined 2 constants, red and blue, and a victim. And in retrospect, I want to make that a 2. I want them to be different from 0. Okay, so that's how I have things. Now, you may remember I developed this mylock interface before. You didn't have to do this, but the way I chose to make this work is if I get the red, I get a mylock that works on the red side. And the way that's going to work is it's going to get the lock, it's going to increment red waiting, and while there are blue threads running, or there are blue threads waiting and red is the victim, I'm going to wait. And then I'm going to, once I get past this while loop, I'm going to decrement red waiting, increment red running, and set the victim to red. So every time a red thread gets through, it sets the victim to red. And every time a blue thread gets through, it sets the victim to blue. Now, there's probably a billion different ways you could have coded this same thing. This is just the way I chose. This is not the way. This is an example that works. Okay. But I thought it was kind of nice to do it this way because we already had a concept of a victim that we'd been working with. And I think it enhances the fairness a little bit. So if the first lock if the first time a thread goes through is blue, then the next time a thread goes through, it's automatically going to get priority, right? Even if that lock had been released. And so it's got kind of a nice fairness built into it. And okay, and then the unlock method is going to say red running minus minus. And then if red running is 0, I can do a signal all. I'm not 100% sure that I need a signal all. I might have been able to get with a signal, but my suspicion is I could get a lost wake up if I don't. Yes. So probably using a different condition for the red and blue might make you go faster if you do it right. I don't know about your case in particular. I think I looked at yours, but I don't think I remember that. But using 2 conditions is certainly an option. All right. And the method had a max threads on there. I don't really use it, so I just returned something, but it's not important. Now, of course, the blue method looks exactly the same, and except that the words red and blue are swapped, which makes me, as a programmer, this bothers me. I don't like to replicate logic. And if I thought about this, I could probably figure out a way to code this without replicated logic. But the problem is when you have replicated logic, is there is a danger that when you replicate it, you don't get it right. And if you find a bug, then you have to fix it in both places. And it's just bad practice if you can avoid it. And maybe with enough thinking, I could make this one not be like that. But I didn't. I just wanted to point out to you that when you see something like this, it should bother you at some level, right? Okay. All right. And this time I chose to return 0 for max threads, I guess, because I didn't pay attention. And I'm not using it, so it kind of doesn't matter. Okay.
What's the point? Why did you have max threads?
Well, the thing was, is okay, so let's look I'll show you why. So I went to build a main method to test this. Now, you should always test your code. When I assign you a code, in addition to having it compile, you should have something there to test it. Because if you don't test it, it's kind of like not compiling it. It's not going to work, right? You should always have a test for things. So I always write one. So in my case, I wrote a red-blue thingy, right? And then I got a bunch of threads. And then I decide each thread is going to either be red or blue. So I just use even or odd to make that decision. And I make that a final variable so I can get at it within my thread. And then I just call lock and unlock. So I have a single interface and I can call lock and unlock this way. That's what I was thinking. Now, the problem is the interface, the mylock interface had another method on there, which I'm not using. And that's the problem. You have to implement all the methods on the interface. And so I was stuck with that. Anyway, I also have an optional sleep in the middle here that happens that depending on how I set the delay, I can sleep for some number of milliseconds just to sort of add some variation in there. And then after that, I join all the threads and I print done. So if I run this, it seems like it's too fair, you know? It just goes 1, 1, 1, 1. Maybe if I try enough times and I put enough sleep in there, it'll get something different than that. But it seems to be kind of almost too fair. Yeah, I've already got the delay in there. So, but that's basically that is a way to do it. Any questions? Okay, we also had two kind of text questions. And in the past X number of times I've taught this course, I've had a grader, and I guess you lose something when you have a grader that I didn't appreciate. And that is when you see the students' answers, you realize, hey, that isn't really the answer, the kind of answer I was looking for. I really wanted them to say something different. And so I learned that I wanted you to say something different, but I can't penalize you for that. So does the FIFO read-write lock need to have a read releases field? Could it instead have a decrement read acquires and unlock and signal all? And most people said, yeah, sure, that should work. And I guess what I was looking for, what I was hoping somebody would say, and I didn't ask it this way, so nobody did, was hoping that someone would say, look at the code on the slide and tell me what I should have done. So let's try that. Okay, so let's go down to 8. And okay, so this is the section where we do it. Okay, and we have the read acquires and the read releases. Right. So if we look at the original code, let's go back to the original code. Right. So the question I wanted to ask is, what would you change to this class to give it that property that we went through, that if once a writer is in place, that the readers stop getting the lock. And I think that it would be as simple as taking this line of code right here, writer equal true, and moving it before the while loop. I think if you just do that, right, I think that's going to accomplish the same thing as having the read acquires and read releases. I think that's really the fundamental thing. And if you look at the code that comes later, right, with the acquires and releases, it does that, right? It asks for the writer first, right? So I think that that's all you really needed to do was move that one line. And that's what I was hoping somebody would say, but nobody said that, of course. Should the reentrant lock, any questions on that? Should the reentrant lock as implemented on the slides use signal or signal all? Please explain your answer. So again, what I was hoping somebody would do was make the connection to the lost wake up situation, right? So we had a lost wake up on the slides. And so we have the lost wake up protocol. And the way this happens is we have a queue, right? And A and B are trying to dequeue an empty queue. And C enqueues, and it signals not empty, right? But before that signal gets processed, thread C comes in and enqueues another. It's thread D comes in and enqueues another item. So what happens is we end up with one item on the queue and one thread waiting to wake up. And the reason this happens is because in this case, we can have two threads enqueuing and dequeuing, right? We needed 4 threads to make this problem work. And with the reentrant lock, right, only the reentrant lock is going to be incrementing and decrementing this hold count. So that this kind of situation cannot occur. We can't, I don't see how to build a lost wake up off the reentrant lock. And that's what you would need to do to validate the use of, to mandate the use of signal all. So that's why I was hoping somebody would make a connection to this particular scenario in this particular slide, but again, nobody did. Yes, Ryan.
For future reference should be tied or should be trying to answer those questions combined with the slide?
That would be great. But what really should have happened is I should have said in the question, I should have said, go look at the slide and tell me based on the slide. That's what should have happened. I should have said, look at the slide. Yes, Reagan. What I'm saying is, no, the code will work with signal all. The question is whether signal all is needed. So are you asking why signal all solves this problem? Because signal works. If signal works, then signal all isn't necessary. Right?
I guess.
So what the question is trying to make you answer is whether signal by itself is adequate, or whether you can get a lost wake up problem because of I mean, I don't say lost wake up problem, but the difference between using signal and signal all, right? That's what you're trying to solve, is whether you have a lost wake up problem that you need to solve. Because in order to, well, in the scenario that we covered before, right? The lost wake up, in order for it to happen, we needed 4 threads. And we need 2 enqueuers and 2 dequeuers. But with the reentrant lock, we don't have that situation. Yes, we have multiple people trying to get that lock, but that hold count is only going to be 1 thread that's trying to increase that. It should not happen with a reentrant lock. I mean, and if what you should try to do is convince yourself, you try to work out a way that a lost wake up can happen with a reentrant lock. And that's what this problem is asking you to do. And if you can find one, if you can find a way that a lost wake up can occur, then you need a signal all. If you can't, then you shouldn't. That make sense? Again, I think I could have asked the question better. But sometimes when you ask a question, you don't have the same perspective as somebody answering the question, and you think.
Signal.
Well, okay, so it's perfectly valid thing for you to do as a programmer to use signal all, just to be on the side of caution. I would support you doing that. The only time, if you're worried about speeding up your application and you think that the lost wake up is causing you think you're waking up too many things and that's causing you performance, then you can explore these kinds of things. But as a programmer, just being defensive and using signal all is a reasonable thing to do. All right. No, signal works here, is what I'm saying. There isn't, unless you can figure out a way to describe to me how a lost wake up could occur, right? I mean, it's easy. We can see how it can occur with the queue, but this is a different situation, and every problem behaves slightly differently. So you can't replicate what happened with the queue there, at least not obviously. So that's what it would take to show that. All right. Okay, any other questions on the homework? All right, good. Okay, let's go back and look at chapter 2.
Peterson's and the filter lock. I think
Okay.
they're big.
All right. Well, what I'm going to do is I'm just going to sort of go through them at high speed and you can stop me. How about that? But first, oh, come on. Today is 9/11.
All those tabs open, not slow your computer.
It might.
So,
I am not what you call a neat and organized person. I mean, I run this course more organized than I think most professors run their courses. But if you look at my office is not more organized looking than most professors' offices. And if you look at the file system and my home directory on any computer that I've been on, there'll be hundreds of things that I don't know what they are. Yeah, well, okay, so so these are both Google Mail, and one of them is my work one and one of them is my personal one. And look, I have a workflow and it works for me. I have a work file. So there's these two systems, right? Random access and sequential access. I work with sequential access. So the way the random access works is you have everything filed by letter. You can go and look up the thing that you need. And sequential access is you have a pile. You start at the top and you keep looking until you find what you need. All right. Um, let's go back. Look, I try to be more organized, but I think to really be successful at it, I would have to go back in time and be younger and but I'm trying to be less disorganized going forward. But I'm going to keep my multiple tabs for at least for now until it really hurts me. All right. This happens from time to time, and then I just have to figure it out all over again. Sometimes I forget things, and because they were only stored on my tab list. But anyway, if it's really important, I write it down somewhere else too. So. All right, so this is mutual exclusion. We're talking about to and end threads. Concurrent programming is hard. We have events. We have states. I don't think any of this is the stuff you need to see. Stop me if I'm wrong. We have these intervals, right, which is a range between two events, right, which can overlap or be disjoint. They can have precedence. We talk about the orderings. We can have repeated events, and we put a superscript for that. We talk about implementing a counter, and we want to make the, yes, Reagan. I have a plan to show you something with the notations if after we get through this. We have the lock and the unlock methods. We have an acquire lock. So always try to use try and finally with locks, of course. We have the definition of deadlock free. We have the definition of starvation free. We have the thread ID class that I made for you. I've since added a couple methods to it, but whatever. Okay, so we have some thread conventions, and we're typically going to leave off these first two lines. We're going to do that most of the time. I is the current thread, and J is the other. And then we have lock one, which is an example of a lock that didn't work. It's based only on a flag. And this can lead to deadlock, right? And then we have lock two, and lock two just sets the victim flag, and then both can get into the critical section. It just doesn't work. I'm sorry. Was that the problem with it? I think it was. Sequential execution deadlocks. That was the problem. Sequential execution deadlocks. Yeah, so if I just go through there and nobody else is coming by, then I can't get through. Somebody else has to push me through. Right? It's like every time you go into a door, you stop and wait for somebody to push you through. Then we have Peterson's algorithm, which solves this by combining what lock one and lock two tried to do, or if we want to think about it in the other way, it combines the flag and the CAN protocol, right? And the realization is we've got flags which only the current thread, which only I read and write, and then we've got a victim thread which we can both write, but we only put in our own unique values. And that combination of things allowed us to build a lock, right? So we can say flag J and victim equal I, and that's going to work.
Peterson's algorithm is just the gentleman's algorithm.
Kind of.
That's all it is.
Yes, it says I raise my flag and then I defer. Hold the door open for someone else. And that's a good way to think about it, right? You think about it as being, and what we found out is if you're greedy and you try to jam your way through the door first, then you've got an algorithm that doesn't work. Okay, and it's starvation free. Now the filter lock is the one that comes next, and the filter lock is just the Peterson's lock repeated n times. Well, if the number of threads is n, then it's repeated n-1 times, right? So a filter lock for 2 threads is the Peterson lock. But a filter lock for 3 threads would be 2 Peterson locks. So the way this works, right? The way this works is each one has a flag, which they called level here. So everybody has their own flag. And then in the victim field, they can all write that victim field. All three of the threads can write that same victim field, and they always write themselves there. And so what happens is if all 3 raise their flags and start this process off, only one of them gets stopped in that first layer, right? One of them gets stopped, becomes the victim. And that one says, does anybody have a flag raised as high as me or higher? And am I the victim? And if both those things are true, I sit, right? And then on the next level, only one of those threads, only one of those threads doesn't get through. The rest of them get through because they aren't the victim. There's only one victim, right? And only the victim is actually stopped. And so each layer of the filter lock stops one thread. And so if I have 10 threads, then I need 9 layers of filter lock because each layer is going to stop one thread until the end when only one thread gets through. Barrett.
It's like holding the door open, except the hallway's just really long.
Something like that,
And,
yeah.
like, one guy's bridge and then like all 9 of these go through, and then one guy's like, no, not you, all 8 go.
Yeah, exactly.
Except it's just on a basis of like how high you're holding your flag is
Yes.
the most.
Reagan.
Okay.
At the last thread to like declare themselves the victim will be the first one to run.
So, okay, so if you go to the very top level and you declare yourself the victim, yeah, you'll be the next one to run. Because anything else that comes in there is going to declare itself the victim, and that's going to free you, if nothing else. I mean, the two ways you get out of that, right, are well, the way you get out of it is the other person who's sharing that top space with you lowers their flag, right? And then you get through. But yes, the first person on the top, the thread on the top should be the next one to get through.
Because you're declaring yourself a victim and letting somebody else go first.
Right. It's starvation free because eventually, you know, nobody else, no matter, you know, if once all the threads that were blocking you get through, then you have to make it next because you can't redeclare yourself the victim. Right? It's going to stop you. Make sense?
Said you were gonna post your version of filter lock on Google. Did you ever?
I thought I did. There's, if you go on, well, it's not on Moodle, it's on the course website. So on the course website, I have a link called codes, and I have I had my IntelliJ workspace there with a bunch of different things, and the filter lock should be, and the bakery lock should both be there. All right. Are we happy with the filter lock? All right. So we wanted to have an even more rigorous definition of fairness. So we came up with this bakery algorithm, Lamport's bakery algorithm. And what we do to make the bakery algorithm work is we have these labels, which are really just integers. And we have a doorway method. And once you get through the doorway, it's kind of like yes, Reagan. You mean re-explain?
What makes this a door?
So there's two pieces to the algorithm. And the idea is once you get through the doorway, it's what I was about to say anyway. Once you get through the doorway, your place in line is guaranteed. That's the concept. Once you get past the doorway part of the algorithm, then your place in line is guaranteed. And your turn is sort of set in stone. If you want to think about this, so it used to be in bakeries, right? You would come in and there would be a bunch of numbers there, and you would take a number and then you would wait for it to be called, right? It's like once you take that number, you've gotten through the doorway. Up until, you could fight to get to that thing to take the number, and there's no fairness there necessarily. But once you have that number, you have your turn. Okay, make sense? So that's what the doorway is. The doorway is getting through there, and then the waiting comes next. Okay, so
Is that the?
yes, the doorway interval is when you establish your position in line. You're battling for the ticket. Okay, and so the way we get our place in line, right, is we need to get our ticket value is going to be found by going through the labels of all the other threads and then finding the maximum and adding 1 to it. Now, it's certainly true that the two different threads could come up with the same value that way, right? Depending on how things happened. So because of that, we have this tuple that we use a combination of that label, that number, and the thread ID. So if that number is equal, then we use the thread ID to break the tie. Which means lower number threads actually get a slight priority, if you want to think about it that way. Now, here's a question for you. What if instead of using this max, what if I just had a single integer and I just incremented that by 1 and stored it as my label? Yeah, well, we can't synchronize it because we're actually writing a lock.
So this is where I had a question that I asked you the other day as well. I don't expect like a whole full-on answer here, but this is, I think I assumed some things were atomic, but they weren't. So
a plus equal.
This is where the consistency models come into play.
Yeah, a plus equal 1 is never going to be atomic.
So either only one take a number.
But again, in order to implement the semaphore, you need a lock. And what we're trying to do is implement a lock. So it's kind of self-defeating.
So if you just have,
What's that?
So you probably
I mean, you could do that, but it would be kind of silly, right? Because you're building a lock with another lock, right? If you already got that capability, then you don't need to do this.
you would just basically like keep incrementing that number, right? And then if,
The problem is, I don't know if you remember this, but from the first slide deck, we had a picture where multiple slides, where multiple things were trying to increment the same counter. And depending on how the delays occurred between the different threads, it was actually possible for the counter to go backwards, right? And that would kill the bakery algorithm, because then it would be like, as you were about to grab the ticket, it got a higher number, right? Yes.
thing.
But it's fairness guarantee. But the point of the bakery algorithm is its fairness guarantee. And so we need that thing to increase. And so that's why we get the max of all of them and add 1, because doing that, we're not overwriting any particular location and we can't go backwards that way. We're only incrementing our own memory, right? So this is the thing that you try to do with these kinds of locks when you're trying to synchronize using just memory like we're doing now. You do it one of two ways, right? You either have a memory location that only you write, or you have a memory location that everybody writes, but you all write your own unique value there, right? Those are the two tricks that we use. And incrementing a single location is prone to race conditions. There's just no way around that. And so we can't use that. Make sense? All right. Okay, so and that's chapter 2. I mean that's chapter 2. Reimagined. Yes.
So bakery lock has a waiting interval, right? But that's only because it has a while loop.
Yeah, so it's got the doorway and the waiting interval. That's the way we defined it.
Waiting if there's some sort of while loop or some sort of.
Yeah, well, it always has a while loop, right? It has the doorway and the waiting interval. So all, if you want to think about it this way, all locks have a waiting interval. And when we developed the terminology for the bakery algorithm, that's what we defined, a doorway and a waiting interval. Right? So this is another thing. When I use terms in this course, right? I expect you to remember those terms and I expect you to expect to be quizzed on them. Okay, sorry. Yeah, so you know what? I have this drink here to keep my throat lubricated, and I'm not using it. All right. All right, so let's go to another thing. We will. Um, I could do that. I could do that now if you'd like. Let's talk about the next homework. Now, the next homework, I recognize that it's kind of tricky. And you know, people have different levels of programming ability. And with something like this, you might be lost about where to start. Um, so let's take a look at, let's just do some planning here. Now what I want to do, so what we want to do is that this hierarchical Peterson lock, we only need to make it work for powers of 2. So 2 for 2 threads, 4 threads, 8 threads, 16 threads, and so on, right? Because this is just an exercise and we don't want to make it overly complicated for no reason. So let's start with thinking about 4, okay? So the way this has got to look, if you want to think about it, is I've got a tree and I've got 0, 0, 1, and 2. And if you want to like imagine this tree is kind of sideways. So 0 is at the top, and on the right it goes to 1, and on the left it goes to 2. That's just my ASCII art, right? I wanted to draw something better for you, but I ran out of time. So we're going to live with my ASCII art. Okay? Okay? All right. Now, if I want, right. So what I'm going to do is when I have this set up, I'm going to have threads 0 and 1 are going to fight for that first Peterson lock. And then threads 2 and 3 are going to fight for Peterson lock number 2. And whichever one of these wins is going to fight for the Peterson lock at the top of the tree, right? So for 4 threads, I need 3 Peterson locks. Make sense? Are you with me? I mean, we still haven't figured out how to make this general yet, right? And sometimes the way to handle a problem like this is to try and start the first few lower levels and see if you can see the trend, and then you can extrapolate, right? And so that's what I'm doing. Are we good? Now, the other problem is, let's say threads 1 and 3 get through here. We need a Peterson lock that works with 1 and 3. So what I'm going to suggest that you do is create a modified Peterson lock. So let's see, I've got a Peterson lock over here, and I was going to set this up ahead of time, but I didn't, so I'll do it now. So what you do is you're going to create another method like that, right? So I have a lock me, and what I'm going to do is I'm going to have this one call that one, right? Simple enough, right? Okay, and I'm going to do the same thing with unlock, right? I'm going to say, oops, I wanted what the clanker was telling me. I don't, AI is such a mixed blessing. See that one, it got it completely right. All right. So you see what I've done there, right? So now when instead of relying on thread ID to get my ID as 1 or 0, I can feed that in to the Peterson lock. Let's go back to my planning session here. So what I'm going to do is I'm going to say, when the winner of this competition here, if of this first one, is going to identify itself as Peterson lock ID number 1, and the winner of this one is going to identify itself as 0, right? So if 1 and 3 get through, right, 1 will try to say lock 1, and 3 will try to say lock 0. And likewise, when this first competition happens between threads 2 and 3, I'm going to say that the 2 is going to try to get lock 0, and the 3 is going to try to get lock 1, because Peterson lock is always between 0 and 1, right?
You go to the leagues first,
Mm-hmm.
and then it's kind of like a tournament where like the winner goes to the next like higher level.
Right. Right. Okay. So that is how 4 should play out. Now, hopefully with that description, you can code the lock for just 4, which isn't the assignment, but it's a start. It's a start in the thinking process on the assignment. So do you think we've got the process for 4? All right, let's try 8. All right, so that was okay, 8 threads. So 0, 1, and I'm going to leave a space, 2, 3, 4, 5, 6. Okay, so that's my tree. Yes, Reagan.
Assignment is to make one that's like as general as possible.
Right.
This is a little wordy, I was just making sure.
So I think if I can make my tree clearer this way, I think I can put a minus sign. Minus sign. And is that clearer? I'm not sure that it is. I don't think it worked. I don't think it worked. All right. So let's keep it the way it is. And so this is going to be 0 and 1, and 2 and 3, and 4 and 5, and 6 and 7. So those are 8 threads, right?
Is there really anything different? You just
It's going to be the same basic concept. We're just repeating it with a higher level of structure, right? So I'm going to say the first ones are going to go for 0. The second ones are going to go for 1 on the Peterson lock. And then likewise, they're going to do that going down. But it's still kind of hard to see how to set that up generally, right? So, but I mean, you can see, okay, this way I could do 4 and I could do 8. And if I asked you to do 16, you could probably plot that out. The trick is to try and figure out, yes.
Theoretically, looking at this from a code point, could you do like a modulo and do like this one goes this way and this one goes this way? To figure that out?
I'm not following you.
So like, you know how you split your red blues between even and odds?
Mhm.
Could you do the same thing here to determine which one goes which direction?
Yes. Yes, you could use even and odds to try and hierarchically get this. And there's as with everything, there's probably a billion different ways you can code this. But one of the things I thought might be helpful, and I confess I didn't think this all the way through, so bear with me if it doesn't just immediately sound great. But you know the heap sort, right? Our favorite algorithm, the heap sort. What you do is you have a tree that's represented as an array. 0, 1, 2, 3, 4, 5, 6, 7, right? And the children of 0 of any node in here, n is going to be 2 times n and 2 times n plus 1, right? That's the way this works. So at the top of the tree, if we have a 0, then the next ones down are 1 and 2. And the next ones down from there are going to be, no, that isn't right. It's plus 1 and plus 2, right? It's plus 1 and plus 2. Okay, so this is going to be 3 and 4. And this is going to be 2 times 2 is 4 plus 1 is 5. And this is plus 1 is 6. So we can that's the same thing I drew up here for 8 threads, but now we can see that's just a linear thing of 7, right? And if oh, I didn't go all the way to 7. I should cut it off there. Now it matches. Yeah. But there are 7 things there that go 0 to 6, right? And so what I can do, so now let's see, how can we map? So we know that we're going to make a tree of size. So if I have 8 threads, I'm going to have 7 things in here. And I guess if I'm going to have 16 threads, I'm going to have 15 nodes in my tree. Now what I need to do is I need to map, and I see how I can just write this as an array here like this. My tree can be represented as an array. I just have to make it the right length and fill it with Peterson locks. Now the question is, how can I take my thread number and map it onto an element of this array? That's the question we have to ask ourselves. So, what I think we do okay, so this is the part I haven't thought through myself. So I'm doing it live, right? So let's try and figure this out. So let's say right, this is our heap sort logic. You don't. You could make an explicit tree in memory. I just think that the heap sort, we don't use a heap sort, we just use the heap sort tree, right? It's just a convenient way to represent a tree. And I think it's going to be really convenient in a minute which is why I set it up. So what I think is going to happen is if I'm on node 6 of the tree, right, and I want to find out my parent, I can just do it with a calculation. So if I divide by 2, so let's see, 3 comes from 2, right? So I can say if it's an even number, I'm going to subtract 2 and then divide by 2, right? So if it's even number, I have a 6. 6 minus 2 is 4. 4 over 2 is 2. There's my parent, right? If I'm an odd node, I'm going to subtract like 5. If I'm 5, I'm going to subtract 1. I'm going to get 4. I'm going to divide by 2, and 2 is my parent. So these two have the same parent. But what I can say is if I'm an even node, I'm going to come into my parent, Peterson lock. I'm just, as a rule, I'm going to come in as ID 0. And if I'm odd, I'm going to come in as ID 1, right? I can make that kind of rule. And that will help me cascade down the tree, right? I can take each step of the tree and I can just apply that logic. So I think that will help. Now, the only thing I have to do is somehow map my thread number to a place here, right? So in this case, and it has to work for 4 and 8, and then we'll check it for 16, and then hopefully we'll be right. Okay, so I've got 4 threads. So with this one, what my thread number over 2, round down. Thread number +1 over 2 +1 is my theory. Okay. I think this formula will get me what I want. So 0 gives me 1. 1 over 2 is 0. Plus 1 is 1. Hello. No, I think the +1 is wrong. Okay, so for 0 and 1, this gives me 0, and then I add 1 and I get there. And for 2 and 3, this gives me 1, and that takes me to 2, right? Does that look correct? Mod 2 isn't what I want because I want 0 and 1 to both go to the same thing.
Oh,
I could just use division, right? Integer division is automatically going to round down. It's automatically going to give me a floor, if you will. I had when I was a graduate student, I was generating Fortran code from this Mathematica script, and it wrote out, x star star parentheses 1 over 2 because it was taking a square root. It was writing out to the 1/2 power. But of course, in Fortran, like in Java, integer divided by integer is integer arithmetic. So 1 over 2 is 0. And my code was giving me the wrong answer. And it was a while before I stared at that and realized, oh, I need 1.0 over 2.0, right? So integer is already going to give you a floor. All right, so we've got that one. Let's see how this one goes. I'm going to say thread num over 2. It's going to be over 2 again because I want to take pairs and map them to the same number, right? And then if I do a +3, I think that takes me to my node. So if I have a 7, 7 divided by 2 is how much?
3.
3, right? +3 is 6, right? So that looks like that works. Okay. So here's what we've got is for 4 threads, we've got 1. For 8 threads, we've got 3. What happens when we go to 16 threads? Let's draw that out. It may be. I don't know. I won't. I won't make any promises or tell you any lies.
Like it's 1 times 2 to the,
Yeah. I just want to write it all out just to make sure I follow my own logic. Right? And now I have 0, 1, 1, 2, 3, 4. And you'll really want to watch this video over and over again so that you can do your homework, right? What was he saying about heap sort?
No, 1, 2, 3.
Yes, it is. Thank you. I was going to eventually have a problem, and you saved me. Commander Tigert has saved us. Anybody here watch Galaxy Quest, the movie? You really should watch it. Yeah, it's one of my favorite movies. Commander Tigert has saved us. Okay, so Reagan thinks that our formula, thread num over 2 plus 5. Unfortunately, it is not. It is plus 7. Okay, so what we're going to do, so when our number of threads is 2 to the n, right, equals 2 to the 4. Right. I didn't know whether you were going to be right or not because I hadn't done this myself. This is me figuring out stuff live, unfortunately. So 2 star star 3 minus 1 is what we get there. And for this one, this is equal to 2 star star 3, right? And to make it even, it's going to be 2 star star 4 minus 2 star star 2 minus 1. That's going to be 3. And for the first one, we're going to get 2 star star 1 minus 1. And it all works. So there's our progression, right? You take the number of threads that you're trying to solve for, take the log to the base 2, or a right shift. You can do a right shift. You know about right shifts? Take a right shift, that's equivalently the log of the base 2, and then you're gonna reduce that by 1, and then you're gonna subtract 1 from it. So if my number of threads, yeah, I'm gonna have to take the log of base 2, subtract 1, raise that to the second power, and subtract 1. I guess another way of saying that is I could just divide by 2, and I could divide by 2 and subtract 1. I guess that's all I need to do. And divide by 2 and subtract 1. So that's our rule. So n over 2 minus 1 is our offset. So for 4 threads, n over 2 minus 1 gives us 1. For 8 threads, n over 2 minus 1 gives us 3. And for 16 threads, it gives us 7, right? Okay, so now if you have a thread number, you know what your index is into that table that the heap sort uses to measure its that the heap sort uses to measure to figure out its children. So you know exactly what child node to go to. And then these formulas tell you how to go from a child node to a parent node and whether you're coming into that node as a 0 or a 1. And between all this logic I've given you, you can code this up. I believe in you. Okay? Yeah, Reagan. Oh. All right, I can probably change it to Thursday. But don't put it off too long. I thought that planning like this with you, for this particular assignment might prove helpful because otherwise I thought some people might be able to get it, but for some people that might be too hard.
It was very helpful. I started doing it, I realized what the question was asking.
And then you said, "Oh no."
I started going, but reading the question, I was like, what does that even mean?
Yeah, so this is hopefully this gives you enough of a head start to figure out the problem. I had a friend in graduate school who got an oral question in physics, and I will never forget the question she got. It was so awful. She's standing in the front of the room full of her professors trying to determine, if she's allowed to stay in graduate school, and you have to pass this test one of two times. Anyway, the guy says, "All right." He says, "You have a parallel plate capacitor. It's infinite parallel plate capacitor, and you have a point charge in the middle. So far, right? It's a standard physics textbook problem. If you've just studied this, that you should be able to do it, right?" And the guy says, "Now, submerge the whole thing in water. And remember that water is polarizable according to the Boltzmann distribution. Find the electric field everywhere." And her response to that was, "What's the Boltzmann distribution again?" Anyway, I always loved that question. Okay. We've got 10 minutes left. One of the things I was hoping to show you, and it may not be enough time. So I have some things that I made. I have a thread unsafe queue. So this is the similar kind of thing that we've seen a million times in this course already. So we have a queue of some fixed size full of integers. We have an initial size that we're, a fixed size queue, and we're initializing it with some number. And while the queue is empty, we're going to yield. And once we have it, we're going to, increment and add. And likewise, we have an enqueue method. And if it's full, we're going to yield. And it's got, this standard way of putting the data in, right? The standard circular queue. We have an isEmpty method and an isFull method and a main method to test it. Now, up here, I have this QI interface that I made. Okay, and it has, can I help?
Oh, sorry, we got,
Oh, no, don't look at that after class. Okay, we have dec, we have enc, we have isEmpty and isFull, right? So those are the things you all have to implement in order to make one of these QI interface things. And I just did it in the most obvious way. So far, there's nothing new here, right? Any questions? All right. And then I made a thread safe queue. And what the thread safe queue is going to do is it's going to have a lock and a not full and a not empty condition. And it's going to create a thread unsafe queue. It's going to have one of these that it's storing internally. And this is going to do a lock, and it's going to say, well, the queue is not empty condition await. It's going to do the dequeue. It's going to signal the not full. So what this is doing is it's separating the concurrent logic from the base logic, right? We have just a thread unsafe queue. We're wrapping something around it to make it safe. And we're just doing it in kind of the ways that we've seen before, right? So far, right? And the enqueue, again, lock, while the queue is full, not full condition await, and then queue.enqueue and not empty signal, and then unlock in the finally. Queue and the isEmpty method, I'm just going to call the queue isEmpty, and the full, I'm just going to call the queue isFull, right? I'm just going to call those things directly. I should probably lock that, but anyway, I'm not going to worry about that right now. And then I have this thing called a queue logger. Now, what a queue logger is going to do This part is different. I have a log entry. A log entry is it's going to implement interface comparable log entry, which means it's got a compare to method on it of type log entry. And this log entry has a couple of different fields. It's got a timestamp, is NQ, which is either going to be true or false. If it's false, it's a DQ. Is start, if is start is false, it's going to be a finish method. It's got an ID, it's got a thread ID, and it's got a value that's getting NQ'd or DQ'd, right? So what this is doing is it's taking all the different parameters of that NQ or DQ operation that we were looking at, and it is just saving them, right? It's just everything is final. It's just going to save them, and it's got a timestamp as well, so we know when it happened, right? And it's got a hash code. So if you want to use it in a hash set, you need both a hash code and an equals method, and you can do that. If you want to use it in a tree set, you need the compare to, and we've got that. All right. And it's got a two-string method, which is going to try to make something that mimics the notation that we've seen before. And you can see sort of the result of this underneath, right? We've got a thread number, we've got the NQ, we've got the value, and we've got the colon here when it's finishing, right? It's very similar to this notation that we've been seeing. And here's a way of, this is a little clumsy, but this is a way of getting a version. If I'm at the end of an entry, I sort of get the start version, and you'll see why I need that in a minute. And what we're going to do is we're going to wrap another queue object. So we're going to take a queue interface object and a number of threads. And what we're going to do is we're going to create an array list for each of the threads that we're going to deal with. And that's going to be a place for each thread to log the events, the NQ and DQ of start and stop events that it's seeing. And so when I call my DQ, for example, I'm going to get my thread ID. I'm going to get the log that goes with my thread ID. I'm going to have an ID for my transaction, which is going to be my log size plus 100 times me. So that's just a way to come up with a unique ID for one of these things. So, and if I have more than 100 threads, or 100 events, this might not work out, but and then maybe I have to put a bigger number there than 100. I don't know. And then I'm going to keep my track of my time the event occurred in nanoseconds. So we get the nanotime. Anyway, what I'm doing is I'm building these logs over the NQs and the DQs. And then over on the thread safe queue, what I'm going to do is in my main method, I'm just going to take like 2 threads, 4 items in each thread, right? And I'm going to set up this thing where I'm going to take two threads here that are just going to NQ and 2 threads that are going to DQ, and they're each going to do 4 items. And then when they're done, right, I'm going to wait for them to be done. And then I'm going to go through the log and then print out the whole log of how those events transpired. So it's going to look just like those things you saw on the slides. And then I have this, and since that output can be a bit much, I have this thing called overlapping. And that's just going to show us things in the log sequence that overlap. Oh, by the way, before I put out the log, right, when I do this get log, I take all of those logs, 1 per thread, and I can put them into a single array list, and then I sort them based on time, right? So I get my entire log of events that occurred based on time, and you're going to see that. Well, here, let me just, I forgot I could do this. I can just hit Control B on that method, and it'll say, I can go through each of the logs. I can add them all to this master log. I can call collections.sort with a comparator that works just on the timestamp, right? And that gives me, am I running the right thing? That gives me an output that looks like this. So those are all the events that I have happening here, all the NQs and DQs. And then I get things that are overlapping here. So I get a DQ on thread 2 starting, and then a DQ of 1 on thread 1 starting, and then an NQ of 0. So you can see that this is similar to the kind of notation we've got, and then we can try to determine whether this is linearizable or whatnot by looking at this. And we don't have time to do that today, but maybe next time we can take a closer look at that. And that's the thing I was thinking that would be useful for us to look at. Okay. Any questions before we finish up? This is a logger. This is a logger for queue objects running on multiple threads. Yes. It produces the kind of output that we had with our notation. It's a history. Yes. So we can look at the history and try to figure out if our code is making sense. Is it sequentially consistent? Is it linearizable? Yes. Sure. Yeah. And you know how to do it now.
Yes.
Good.
70%.
70. Hey, you can't ask for more than. What is it Doctor Who says? One good solid hope is worth a cartload of certainties. You have a question?
Could you save in Java? Could you save that save individual logs so you can keep track of what went on at what version of what program? I mean,
Yeah, oh, you could save additional information, meta information in the log about versions. Yeah, you could potentially do that. Yes. All right. I will see you not next week. Next week you will have a guest lecturer.